In the previous few lectures, we have discussed the line element and the metric tensor. And we have seen that our discussions were limited particularly to the Cartesian coordinates and the n-dimensional Riemannian space. Now, in fact, in the forthcoming lecture and in the present lecture, we are going to discuss the same thing but in particular coordinate system, or you can say the orthogonal curvilinear coordinate system. You know, apart from the Cartesian coordinate system, there are two other important orthogonal coordinate system, and those are actually the spherical polar coordinate system and the cylindrical coordinate system. So in this present lecture, our aim is to express the line element and the metric tensor in spherical polar coordinates. And in the next lecture, then we will see the same thing in the another important orthogonal coordinate system, which is cylindrical coordinate system. So in fact, you will see in this lecture how we can transform the expression of the line element and the metric tensor from the Cartesian coordinate system to the spherical polar coordinate system. So this is just a transformation problem. If you know the line element and the metric tensor, particularly in Cartesian coordinate system, how you can find these things in the spherical polar coordinate system. One thing I would like to share with you that this is a very important problem, and if you will study the general relativity, particularly the Einstein's momentum tensor, then you will find the application of this problem very much. In fact, I have a series of papers in the reputed journal where I have used this concept which I am going to discuss, and this is also very important for your examination purpose. So let us start with the definition of the line element in Cartesian coordinates, particularly in the three-dimensional Euclidean space, which you have already seen in the previous lecture. You have seen that the line element ds is defined by this quadratic equation. This is ds square equal to dx square plus dy square plus dz square. In fact, if you consider for convenience that x is equal to x1, y equal to x2 and z equal to x3. Remember, this is not x square, but this is just for y. x2 means y and x3 means z. This is written only for convenience. Then in this symbol, this ds square you can define like this. This is dx1 square plus dx2 square plus dx3 square. And we have also seen in the previous lecture the definition of this line element or the expression for this line element in the n-dimensional Riemannian space. And we have seen that in n-dimensional Riemannian space, this ds square is equal to summation over I from 1 to n and summation over j from 1 to n gij dxi times dxj. In fact, if you use the Einstein summation convention, then there is no need to write the sign of summation. It is obvious that the summation is implied for the repeated index. So without writing the sign of summation using the summation convention, you can also write this expression in this manner. This is ds square equal to dij times dxi times dxj. Now, if you want to write this equation too, particularly in Cartesian coordinate system, that is in three-dimensional space in Cartesian coordinate system or Euclidean space, then what will be this equation you can easily see. In fact, in 3D space, Gij, as you know, see here, this Gij, I have written it here, is a covariant tensor of second rank, and the space is three-dimensional. So you know, if the tensor is of second rank, a space is three-dimensional, so the number of components of this tensor in this three-dimensional space will be 3 to the power 2, that is dimension of a space raised to the power rank of the tensor. You have seen this thing in the early lecture on this tensor analysis. And so the components of this Gij, that is the metric tensor Gij, in the matrix form you can write this is equal to G11, G12, G13, G21, G22, G23, G31, G32, G33. These are the 9 components of this metric tensor. So when you will expand this RHS of equation 2 by taking the summation, what will be your result? You can see. In fact, G11, when you take 1, it means I and j both are 1. So in this condition, the first term will be G11 dx1 times dx1. See here, dx1 times dx1, because I and j both are 1. So this will be dx1 times dx1, and that can be written as dx1 square. Similarly, if you take I and j both equal to 2, that is, you are talking about this diagonal element of this metric tensor, then there will be dx2 into dx2, so this will be dx2 square. And when you will take I and j both 3 equal to 3, then this will be g33 dx3 square. And after that, you have to take I equal to 1 and j equal to 2, that is g12. Then this will be g12 dx1 dx2. And in the similar manner, you can see the other terms, and you can understand from this matrix for the different values of I and j. Now we will compare this equation number 3 to the equation 1 in Cartesian coordinate. You can see in the equation 1 in RHS there is only dx1 square plus dx2 square plus dx3 square. It means only the terms containing I and j equal are non-zero, and all other terms in which I and j are different, those are not present in equation 1. It means you can say that this Gij, this will be equal to 0 if I is not equal to 0, because all these terms will be 0. G12 is 0, G13 0, G21 0, G31 0. And you also know that this is a symmetric tensor. So if G12 is 0, so G21 will be also 0. So all these terms in which I and j are different are 0. It means Gij is 0 when I is not equal to j. But at the place of G11, if you compare this result with this equation 1, you see that at the place of G11 there is 1, at the place of G22 there is also 1, at the place of G33 there is also 1. Because in RHS of equation 1, only dx1 square, dx2 square and dx3 square is present. So what does it mean? It means G11, G22, G33, all these 3 are equal to 1. So we have evaluated the value of the different elements of this metric tensor. You can see only the diagonal elements are non-zero, and that those are actually equal to 1, and all the off-diagonal elements of this metric tensor is equal to 0. Now, as I have told you earlier that if you know the expression for the line element in Cartesian coordinate, then by the use of transformation equation, we can transform the expression for the line element in any other coordinate system. Here our aim is to transform it into the spherical polar coordinate system, but before that, first of all, we consider there are two coordinate systems. One is unprimed coordinate system having the independent variables like xi, xj, and so on. And another is the primed coordinate system where you write the independent variables with the primed symbol, that is x prime mu, x prime nu, and so on. So if you consider that the components of this metric tensor Gij in the primed coordinate system is G prime mu nu. What is this G prime mu nu? These are the components of the metric tensor Gij in the primed coordinate system. As you know, this Gij is a covariant tensor of second rank. So by using the law of transformation of covariant tensor of second rank, you can say what will be these components G prime mu nu. You have already studied the transformation law for a covariant tensor of second rank in the previous lecture. So I hope you understand these things clearly. So G prime mu nu, this will be equal to, according to the transformation law, this will be equal to Gij times del xi by del x prime mu times del xj by del x prime nu. You know this. Now, when we will talk in this problem, about this problem, you can see in the present context, since Gij is equal to 0 if I is not equal to j, and Gij is equal to 1 when I is equal to j. You can see here G11, G22, G33, all these are equal to 1. So in fact, this transformation equation in this condition may be written like this. This is summation over I 1 to 3, because we are considering only the three-dimensional space, and this expression has been written for the n-dimensional space, but we are now talking about the three-dimensional space. So here the sign of summation have the limit 1 to 3, and we have written here Gii because Gij will be equal to 0 if I is not equal to j. So this will be Gii del xi by del x prime mu times del xi by del x prime nu. This is the expression for G prime mu nu. You can see. And this expression is written like this, and this is nothing, this is same as I have written it here. So this is just a repetition, you can see. And let us say this is your equation number 4. And here I have dropped Gii. Why? You know, because here there is no repeated index, so no summation, and its value is equal to 1. So Gii has been dropped in this equation number 4. So this is our working equation, and from this we can transform the line element from the Cartesian coordinate system to the spherical polar coordinate system. Now see this figure. Actually, I have shown here the three rectangular coordinate axes x, y, and z, and there is a point P in a space, you can see, and I have assumed that the Cartesian coordinates of this point P are x, y, z, and the spherical polar coordinates of this point are r, theta, phi. I hope you have an idea of the transformation equation between the Cartesian coordinates and the spherical polar coordinates. But just for a reminder, I would like to say you, if you want to transform this x, y, z in terms of r, theta, phi, what you do actually? Actually, for this, we draw a perpendicular PA on xy plane, and then we draw a line AB parallel to y-axis, so it will intersect the x-axis at B at an angle 90 degree. This angle does not appear like pi by 2, but it is pi by 2. And similarly, when you draw a line AC parallel to x-axis, then again this angle will be pi by 2, and join this origin O to the point A where the foot of this perpendicular falls on the xy plane. Then this OA is actually the projection of this OP or R in xy plane, and we draw a line PD parallel to this projection OA, and so this is also pi by 2. This angle is also pi by 2. Then by applying the geometry for a right angle triangle, you can see you know the spherical polar coordinate r, theta, phi are what in this figure. This OP is actually equal to r, and the angle made by this radius vector r with the z-axis is theta, and the angle between the x-axis and this projection OA is equal to phi. So these are r, theta, phi, which are spherical polar coordinates of this point P. Actually, in the topic curvilinear coordinate in my previous lecture, you can watch my video to see the transformation equation between x, y, z and r, theta, phi. I have described these things earlier in the lecture on curvilinear coordinate system, and you can watch those videos. So after making a simple algebra, you will find, and I hope you have an idea of these transformation equations, that this projection OA is actually equal to x, OC is equal to y, and this OD is equal to z. In fact, this is z. This is z. And the transformation equations are x equal to r sine theta cos phi, y equal to r sine theta sine phi, and z equal to r cos theta. Actually, you can prove this by taking the right angle triangle AOB and then the right angle triangle OPD. You can derive these results. But you have to remember it. Always the derivation is not needed. So in solving the problem, you must remember these transformation equations. Now here I have written the Cartesian coordinates x, y, z. But as you know, for convenience, we actually write sorry. Now see, we can we have to add some pages because there is limited page, so I am adding the page. Now see, these are the transformation equations, but for convenience here I am writing the convenient symbol for x, y, z. Here there are two coordinate system. Let us say our unprimed coordinate system is the Cartesian coordinate system, and at the place of prime coordinate system we consider our spherical polar coordinate system. So in this condition you can take let x equal to x1, x equal to x1, y equal to x2, and z equal to x3 we consider. And similarly, if you consider that our spherical polar coordinate system is the prime coordinate system, in fact in that condition you can write x1 x prime 1, this is equal to r, x prime 2, this is equal to theta, and x prime 3, this is equal to phi. We consider for convenience. Now, in this condition, see this equation which we have actually written here in this equation number 4. So, using equation 4, what will be the value of g prime mu nu? G prime mu nu, it means we have to find the three components of this g prime mu nu. First of all, we will take mu and nu both equal to 1, then we will take mu and nu both equal to 2, then we will take mu and nu both equal to 3. So you can find the value of this g prime mu nu on the basis of this equation 4 in the light of these symbols. So you can see it here. So from equation 3, if you want to write g prime 1 1, g prime 1 1, it means see the equation. You are taking mu equal to 1 and nu equal to 1, and I will be equal to 1, 2 and 3, because you can see here the limits for I runs from 1 to 3. So what will be your result? You can see when you will take I equal to 1, then this will be del x1 by del x prime 1 times del x1 by del x prime 1, and plus, because there is summation, now take I equal to 2. So del x2 by del x prime 1, del x2 by del x prime 1. See here, mu and nu are fixed. Mu is equal to nu here, and both are equal to 1. So you can see that in the denominator, since the superscripts are mu and nu and those are fixed at 1, but I runs from 1 to 3. So in this condition, we can write the third term del x3 by del x prime 1 del x3 by del x prime 1. Now simplify it. You can see the first term can be written as del x1 by del x prime 1 whole square, and plus the second term is del x2 by del x prime 1 square, plus third term will be del x3 by del x prime 1 whole square. Now see, in fact del x1, this is in fact x1 is x, so you can write it x, del x, and del x prime 1, see here, x prime 1, this is equal to r. X prime 1 is equal to r. So this will be del r square plus, you also know x2 means y, so this will be del y by del r, because x prime 1 is r, so this is del y by del r square. Similarly, the third term will be del z by del r square. Del r square. Now, see this transformation equation. From here you can find del x by del r, del y by del r, del z by del, since there is partial differentiation with respect to r. So if x is equal to r sine theta cos phi, so what will be del x by del r? Can you say? Del x by del r, this is very simple. This will be simply sine theta cos phi. And similarly, del y by del r, you can see this will be sine theta sine phi. And del z by del r, this will be simply cos theta. You can easily see. So substituting the values of these partial derivatives using that transformation equation, we can write del x by del r, this is sine theta cos phi square plus second term will be what? That is, you have seen just now, sine theta sine phi square, and plus the last term is cos theta, so this will be cos theta square. Now simplify it. The simplification is very easy. You can see in the first term and the second term, this sine square theta will be taken as a common factor, and the remaining terms are cos square phi plus sine square phi, and plus last term, this is cos square theta. But you know this cos square phi plus sine square phi is 1, so this is simply sine square theta plus cos square theta, and that is equal to 1. It means the component G prime 1 1 of the metric tensor in the spherical polar coordinate system is equal to 1. G11 prime, this is equal to 1. And you can also see in the similar manner that this G11 you have already seen earlier, this is also equal to 1. This is also equal to 1. Now our aim is to find G prime 2 2. Again see this previous equation. When you will find G prime 2 2, it means you are taking mu equal to 2 and nu equal to 2. And for I there will be summation from 1 to 3. So in the light of this equation 4, again you can find the value of G prime 2 2. See the result. Again, from the same equation 2, we can write G prime 2 2. This will be what? For I equal to 1, this will be del x1 by del x prime 2, because now mu is equal to 2 and nu is also equal to 2. And this will be again del x1 by del x prime 2. And plus, you can say the next term, this will be del x2 by del x prime 2 and del x2 by del x prime 2. And now I equal to 3. So this will be del x 3 by del x prime 2 del x 3 by del x prime 3. Del x prime 3. You can see. Again, instead of this x1 we will write x, instead of x2 we will write y, and instead of x3 we will write z. And x2 prime, you can see, you have assumed that this x2 prime is what? x2 prime is theta. This is actually theta. So you can write this is equal to what? This is del x by del theta square plus del y by del theta square and plus del z by del theta square. Now again we will find the values of these partial derivatives on the basis of the transformation equation which we have seen earlier. See here, this is your transformation equation, x equal to r sine theta cos phi. Now you have to find del x by del theta. Since differentiation is partial, so only sine theta will be differentiated and r cos phi will be taken as a constant factor, and dc of sine theta will be cos theta. So del x by del r, can you say what will be that? That is simply r cos theta cos phi. R cos theta cos phi. I will write these things directly there. See here, understand here, and I will write at that place directly. Then you have to find del y by del r. Del y by del theta. That will be r cos theta sin phi. And del z by del theta, see here, this will be minus r sin theta. Have you understand? Now put these values in your equation here. So del x by del theta, I have just shown you the transformation equation from which you find this will be what? This is r cos theta cos phi, and there is square plus del y by del theta. You have seen this is r cos theta sin phi and the square, and plus del z by del theta. You have seen this is minus r sin theta square. Now simplify it. You can see r square is a common factor. It is present in each and every term. So you can take this r square as a common factor. And in the first two terms, cos square theta will be also a common factor, but in first two terms. So in first two terms, take this cos square theta as a common factor. So the remaining terms are cos square phi plus sin square phi and plus. Now see the last term. You have taken already r square as a common factor, and so only there will be sin square theta here. Due to squaring, this minus will become plus. And now see what is your result. This is r square. Now this cos square phi plus sin square phi is 1. So this is cos square theta plus sin square theta. Is it okay? And this is again equal to 1. So this is simply equal to r square. So the value of this G prime 2 2, this is equal to what? This is equal to R square. This is R square. These values are very important, how we can transform the values, the components of the metric tensor from Cartesian to a spherical polar coordinate system. Now, after getting the value of G prime 2 2, finally we will obtain the value of G prime 3 3. G prime 3 3. So, see. Now I am not showing that previous equation. You know what will be the result. Now G prime, sorry, see here. G prime 3 3. It means now you are taking mu and nu equal to 3. And from that equation 4, you can say after taking the summation, our result will be what? Del x1 by del x prime 3 times del x1 by del x prime 3 plus del x2 by del x prime 3 times del x2 by del x prime 3 plus del x3 by del x prime 3 times del x3 by del x prime 3. Now again we will write x instead of x1, and so this will be del x, and you know x3 prime. x3 prime, you can see here, we have assumed that x3 prime is equal to 5. See here, this is actually 5. There is some color problem. So this will be phi. This is del phi square. Similarly, this x2 is y, so this is del y by del phi square, and plus del z by del phi square. Now again see the transformation. I am not turning the page. X equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta. And from here you can easily find these partial derivatives. See here, del x by del phi, and since derivative is partial with respect to phi, so this will be r sin theta minus sin phi. So this is minus r sin theta sin phi square, and plus, now see, del y by del phi. Since here is sin phi, at dc of sin phi will be cos phi, so this is r sin theta cos phi square, and plus, now see, since z is r cos theta, so it is independent of phi, and therefore del z by del phi will be equal to 0. So the last term in this case will be equal to 0. So what will be your result? You can see again r square can be taken as a common factor, and now see, sin square theta is, you can also take this sin square theta as a common factor. See here, This is in fact 0, and we can take this r square sine square theta as a common factor, and then there will be sine square phi plus cos square phi, and this is equal to 1. So finally this is r square sine square theta, and therefore you can say g prime 3 this is equal to r square sine square theta. So we have obtained the diagonal elements of the metric tensor in the spherical polar coordinate system. Now we will try to find the off diagonal components. And for this we will again see the same transformation equation. So see that transformation equation as you have defined it earlier in this equation number 4. See here, in fact there is a color change here. So in this case, if you want to find g prime 1 2, so you will take here 1 instead of mu and 2 instead of nu. So let us see what will be this value. In fact there is some defect. Let us there is some problem here. This color will be automatically changed. I am writing here. You can see if we try to find g prime there is some problem. Now it will be okay. See, in fact working for a long time the problem arise. This is G33. Now see, now it will be okay perhaps. Now see here. Now we want to find g prime 1 2. It means you will take mu equal to 1 and nu equal to 2. See, at the place of mu we will always write 1, at the place of nu we will always write 2, and again the summation will run for I from 1 to 3. So what will be our result? You can see it here. But there is some defect in page. See here. I am just turning the page. That will be okay. See here. Now it is okay. I am adjusting the page. Now see. Yes. This is G prime 1 2. G prime 1 2. You can see this will be del x1 by del x prime mu, but mu is 1. So this will be del x prime 1 and del x1 by del x1 by del x prime nu, but nu is 2. So this will be del x prime 2 and plus del x2 by del x prime 1 del x2 by del x prime 2 del x prime 2 and plus del x3 by del x prime 1 and del x3 by del x prime 2 del x prime 2. Now see, del x1 is x, so this is del x, and x1 x prime 1, this is in fact r, so this is del r, and again this will be del x by del x prime 2. X prime 2 is in fact theta, so this is del theta. I hope you understand. And del x2 is y, so this is del y by del r times del y by del theta, and plus this is del z by del r times del z by del theta. And again see that transformation equation, x equal to, I am writing it in bracket, r sine theta cos phi, y equal to r sine theta sine phi, and z equal to z equal to simply r cos theta. This is r cos theta. And from here you can see del x by del r, g prime 1 2 equal to del x by del r. See here, del x by del r, this will be simply sine theta cos phi. So this will be sine theta cos phi times del x by del theta. See here, del x by del theta, this will be r cos theta cos phi, r cos theta cos phi, r cos theta cos phi, and plus again see del y by del r, this will be sine theta sine phi, sine theta sine phi, and del y by del theta, see here, this will be r cos theta sine phi, r cos theta sine phi, and plus del z by del r. See here, del z by del r, this is simply cos theta, and del z by del theta, this will be minus r sine theta, minus r sine theta, minus r sine theta. Now you can simplify this result. In fact, you can see from this from these equations that r is a common factor here. R is present in each and every term, and in the first term there is sine theta cos phi, cos theta cos phi. So cos phi will be a common factor, r sine theta cos phi. In fact, you can write this expression like this. This is just r sine theta cos phi into cos square phi cos phi, not cos phi, but cos theta, r sine theta cos theta. We have taken it as a common factor. In first term there will be cos square phi. In second term there will be sine square phi, and in the last term there will be minus 1. And since this is equal to 1, so this is r sine theta cos theta into 1 minus 1, and then which will be 0. So this result is 0. So finally we get that this g prime 1 2 is equal to 0. So you can see when mu and nu both are different, then this component of this metric tensor is equal to 0. But as you know that this metric tensor is a symmetric tensor, so actually g prime 1 2 is equal to g prime 2 1, because this is a symmetric tensor, and therefore this will be also equal to 0. In fact, in similar manner, if you will try to find the other components of this metric tensor when mu and nu are different, you will find that all of them are 0. So I am not working out the calculation to get the values of those, but you can see, you can try. Similarly, you can write that g prime 1 3 will be equal to g prime 3 1, and this is equal to 0. And similarly, g prime 3 2 is equal to g prime 2 3, and this will be also equal to 0. So now you can find on the basis of this, you can say that this g prime mu nu is equal to 0 if mu is not equal to nu, you can say. And so in this condition, we can find now the line element which we have defined earlier. So in the prime coordinate system, that is in the spherical polar coordinate system, you can say here this ds square will be now equal to what? This will be equal to summation mu equal to 1 to 3, mu equal to 1 to 3, g prime mu, because all other are for all other values of g prime, for different value of mu and nu are 0. So this will be g prime mu and dx prime mu times dx prime mu. And you can write this expression as g11 prime dx1 dx prime 1 dx prime 1 plus g prime 2 2 dx prime 2 dx prime 2 plus g prime 3 3 dx prime 3 dx prime 3, because mu runs from 1 to 3. So this is simply g prime 1 1 dx prime 1 square plus g prime 2 2 dx prime 2 square plus g prime 3 3 dx prime 3 square. But in a spherical polar coordinate system, you have just calculated the values of the components of this metric tensor, that is g prime 1 1, g prime 2 2 and g prime 3 3. You can see all these values here. This is in fact your g prime 3 3, which is r square sine square theta. Again you can see this is your g prime 2 2, which is r square, and this is your g prime 1 1, which is actually 1. So you can put the values of these components of the metric tensor, and you know x prime 1 is r, x prime 2 is theta, and x prime 3 is phi. So what will be this? This will be in fact 1 into dr square plus, and this is r square, g prime 2 2 is r square, so this is r square d theta square, and plus g prime 3 3, this is r square sine square theta, and x prime 3 is what? X prime 3 is phi. So this will be in fact plus r square, this is d phi square. This will be d phi square. So ds square is simply dr square plus r square d theta square plus r square sine square theta d phi square. This is the expression for the line element in the spherical polar coordinate system. And in this way, you can transform the expression for this line element in Cartesian coordinate system to the spherical polar coordinate system. Although in this lecture I have derived this result, but you have to remember it. To solve a numerical problem, we have to write this expression for the line element in the spherical polar coordinate directly. So you must remember it. Now after getting this value of a metric tensor, the line element in a spherical polar coordinate system, now our aim is to find the metric tensor in a spherical polar coordinate system. Metric tensor in a spherical polar coordinate system. So the metric tensor in a spherical polar coordinate system. A spherical polar coordinate system. Now I am not writing G prime. You can write Gij, but remember this is not the metric tensor in Cartesian coordinate system, but in a spherical polar coordinate. You write the sign of prime when you have to compare two coordinate systems. Cartesian was unprimed and polar was primed, but here there is only one coordinate system, so there is no need to write prime. So Gij, you should think these are the components of a metric tensor in three-dimensional space in a spherical polar coordinate system. So we will write its component like this: G11, G12, G13. In matrix form I am writing this. And G21, G22, G23, and G31, G32, and G33. But you have seen that this G11 in a spherical polar coordinate system is 1, and G12, G13, all these are 0. G21, this is also 0. G22, this was R square, you have seen. And G31, this is 0. G32 is also 0. But G33, this is R square sine square theta. So in matrix form, you may write the metric tensor in a spherical polar coordinate system like this. Don't confuse that I have not written here the sign of prime sign, because I am considering only a spherical polar coordinate system. So if you say that Gij are the components of the metric tensor in a spherical polar coordinate system, then you can write the symbol without prime. And these are the components in matrix form for the metric tensor in a spherical polar coordinate system. So I hope you have understand the concept which I have discussed, how we can transform the line element and how we can obtain the metric tensor in the spherical polar coordinate system.